to get the best of me.
All right, well, give me a minute just to get some things opened and set up. All right. So I've got that out of the way. That is there. Now I am going to join the meeting from my tablet. Meetings. All right, so there should be let's see, manage participants. Okay, so there's my co-host link. And then I need to mute. Great. I'm still trying to work out the logistics of two devices. I've got a tablet that I can write on, but it is, how do I disable the audio on this? This was working yesterday, and now it's not. Okay. So there. And mute that one. Okay, that's done. Then I'm going to share the screen on this one. All right, so. Okay, everyone. Looks like we are set up. Here's what we're going to do today. First, I'm going to go over just a few logistical things and a reminder of how we submit assignments. I thought, is it unmuted again? I think it is. My second thing is unmuted.
I'm not hearing any echo.
What?
You're fine. I'm not hearing any echo. You're fine.
Oh, okay. All right, thank you. Yeah, it's still showing that I'm muted.
Maybe it's the audio on the tablet.
What?
You're in the meeting on the tablet, right?
Oh, it's the audio on the tablet that's echoing. Got it. All right, let me turn that down. It won't. Well, it's low enough that we won't get a lot of echo, or at least you won't get any echo and I'll get very little, so I can live with that. All right. One thing I want to do is, there were some questions about assignment submissions, so Blackboard, this will go smoother next time. It's still just learning it. All right, for submitting assignments, all of the new assignment, or all of the ones that are due soon, Let me share this screen. Okay, so now I've got multiple things open. All right, in Blackboard, any of the newer assignments, at least for the next few weeks, I haven't updated the full semester, but any of the newer assignments, when you go in there, besides seeing the PDF of the assignment, you're going to see a place where you can either write a submission, which you won't do, or you can attach some files. So be doing that. That's how you're going to submit everything. Ideally, submit your computer assignments as PDFs. Submit any handwritten work as a scan or photo. If it's multiple pages, try to zip all of those photos into one zip folder and upload that. It's just easier in Blackboard, but do whatever you need to do. Another thing I should say about the logistics of this class going forward, did you see that? Okay. Everybody sees that on Blackboard? All right, it looks like it's showing up on both of my devices. Then I'm going to resume the share of this screen in OneNote, and let's see what I see here. All right, why? No, I don't want to pause that share. Okay, then I want to see. This is working. I want to share this screen. Why can I not get back to my tablet?
I mean, you're on your tablet for us. You're looking at the solution to one of the questions in the activity.
Oh, you're seeing it? Okay, I was trying to figure out why it's not showing on my laptop screen.
No, it's here, but we're looking at the solution to one of the activity questions right now.
Okay, let me just give me one more second to see if I can get these two screens synced up.
I don't know about anybody else, but I'm currently looking at Blackboard, the browse my computer, write a submission screen.
I am not looking at that.
So if you go to the top, there's a drop down that says View Options. You can choose between the two screens that Small is sharing.
Oh, I'm sharing two screens right now.
Now I'm looking at the other one. Okay.
Okay. I see what's going on. Okay.
Yeah, I don't have that selection option. That's interesting. I mean, I'm on a tablet, but I don't have that selection option.
Yeah, the Zoom for tablets is a little bit different from Zoom for desktops. And I tried contacting Zoom's tech support, and let's just say that traffic on their tech support site is as busy as their share trading, because many, many businesses and nonprofits are using them right now. Okay, a general statement about department policy and everything. You've probably heard a lot of contradictory things. Different colleges have at different points announced very different things. I don't know what the professors for your GE classes are doing. I know that the administration in different colleges has done different things. What I can say is that all physics lecture classes are online. A few physics lab classes are in person. Not all, but a few. And it's only lab classes at the 2000 level and above. And even those, now all of them are in person. The only reason any of them are in person is that these are classes where you've got one or two sections, which means that in a given week, very few people are touching the equipment. Whereas in the intro labs, you know, we run 18 time slots a week, 2 people in each lab group in each time slot. So there could be up to 36 people touching a piece of equipment in a week. So many, not all of your upper division labs will be running. None of your upper division theory classes will be running in person. I think that the GE classes are going to all be online, but there was some confusion for a while. There's a whole bunch of behind-the-scenes stories about why that is. We can talk about that some other time. All you need to know for now is that no matter what someone in another department says, the only thing that matters, the only thing that matters for physics and astronomy classes is what our department chair says. So if somebody says to you, oh, but my friend in this other college heard, ignore it. That might apply to the class taken by their friend in this other college. Doesn't apply here. Are there any questions on anything relating to the big picture, the whole situation, what we're going to do?
No.
The last thing I'll say is they're not yet announcing that whether or not that we're going to have classes in person after spring break. I really don't see it happening, mostly because no one else is planning to do it. I mean, it's always possible that the health situation will improve drastically. Great. I have a feeling that although we're not going to have classes after spring break, they're going to delay that decision as long as possible. We'll just have to be flexible.
Are they still going to do midterms online? Or, because we have Salik's midterm in like a week and a half.
He's going to do that online. I can think of two ways to do an online midterm. One is that you type your answers into Blackboard or some other site like that. He might do that. What I did on Friday for my Physics 2530 class is I uploaded the midterm at 10 a.m. I gave them 2 hours to do it, photo or scan their solutions, and upload. But you'll have to ask him. But you should assume that most of your classes will still have midterms, and while the specific rules and details will vary, it will probably be something like that.
Okay.
All right, as far as optics, here's what we're going to do today. I want to go over the solutions to the activity because we need to get some of these concepts so that we can do what's coming up. And then I want to give you some time to start on the next ZMAX assignment. You should be able to share screens with me. And I think that's what we'll also do for office hours. If you have a ZMAX question, and you totally don't have to come to campus. If you are on campus, fine. We'll sit far apart from each other. But the other thing you can always do is request that I send you a Zoom link, and then you can do a screen share with me. But for now, I want to go over the solutions to the activity. And so, because we need that for next time, what we had in the activity was we wanted to understand why we often factor out e to the minus I omega t. And we considered a wave that looked like this. The sum of two individual waves with their own amplitudes and k vectors. But the key thing is that we are evaluating the field at one point in space. And so we have to work with this expression. So the first thing we do is we try taking the real part and adding everything up, and we get this messy combination of cosines. What I want you to notice is that the k dot is the k dot r and how that's done. Some people always ask me, are things different for waves? Are things different for complex waves? Math is math, dot products are dot products. K dot R is just KX plus KY plus KZZ, whether we're dealing with complex numbers or real numbers, waves or fields or static fields or particles or whatever. Then the question was, would we get the same result if we had written the wave like this with the e to the minus omega t factored out? And there's a couple of ways to see that. One way to see that would be just to say, look, we factor it out, but we could always multiply it back in. The other way is that we could do the some trig identities. We could, I'm only going to do one of the cosines, but we could always write cosine omega t plus I sine omega t times cosine of k dot r plus I sine k dot r. And if we do that, then let's just look at what the real part of this expression is. We're going to get real terms if we multiply the cosines and if we multiply the I sine terms. We'll get imaginary parts if we multiply cosine by I sine or I sine by cosine. But if we just multiply the things that give us a real part, then we're going to be left with cosine omega t cosine k dot r, and oops, I just realized this should be minus I sine omega t because it's e to the minus I omega t there. And then we're going to have minus I times I, which is 1. So we get what I just wrote out here. And then we have to look in a trig textbook. But if we look at a table of trig identities, the cosine of a difference is exactly equal to this. All right, so factoring out the cosine doesn't really, factoring out the time dependence doesn't really change anything. But now let's go back to the exact expression and let's just explicitly square it. So we're going to be squaring this sum here of a cosine and another cosine. We're going to get 2 cosine squared terms, and then we're going to get this product of cosine. Now, when we take the time average, because the time average is the only thing that we usually measure. We usually just measure the number of photons detected in some time interval way longer than one period of oscillation. I got the question last time, are we ever measuring something instantaneous? Well, in some sense, we're always measuring something instantaneous. If we watched our detector for a very, very short amount of time, either a photon would be detected and another electron would be going through, or it wouldn't. So if you could somehow watch your electronics really fast, yes, your electronics are measuring something instantaneous. There's either an electron going through or there isn't. But you don't normally detect one electron at a time. You're detecting an integrated signal. You're detecting a signal over a millisecond, a microsecond, maybe a nanosecond sometimes. So that's always going to be some averaging. And the average of cosine squared is just 1/2. We could do that down here where we take cosine squared of some constant minus omega t, and we use the trig identity for cosine squared, and we get this. We've got a constant term here, and then a cosine of 2 omega t and a constant in there. And this term is 0 because the integral of cosine 2 omega t over 1 period is 0. You're just integrating this, basically. This is 1 period. This is 2 periods. And so the average of this is 0. And so then we've just got this term, which the integral of 1 dt from 0 to big T is just t evaluated from 0 to big T is big T, which cancels out the term there. And then we've got this messy product. And that messy product takes some work. So what we're going to do is we're going to start by taking this cosine and write it in terms of exponentials, and we get the product of sums of exponentials. And that's here. And when we multiply these two things, we get 4 terms. Now, in some of these terms, we've got e to the minus I omega t times e to the minus I omega t. So then you're going to get e to the minus 2I omega t. But in other terms, you've got e to the minus I omega t times e to the plus I omega t, or e to the plus I omega t times e to the minus I omega t. You might look at this and say, well, there's a minus omega t everywhere, but remember that there's a minus sign here and a minus sign there, and they cancel, and likewise there and there. And so 2 of these terms have these rapidly oscillating functions in them, and 2 of these, the time dependence has gone away. And those terms are still oscillating in space, but they're not oscillating in time. So if we take the time average as something that doesn't change in time, we've got a function that's just one number at all times. Whatever that number might be, it's the same at all times. This term, of course, changes depending on what our value of r is. Looking at it at different points in space, we're going to get a very, very different number. But we didn't ask what the position average was. We just asked what the time average was. And the time average is just this and this. And furthermore, these 2 terms, when we add them up, we're going to get 2 times cosine of k1 minus k2 dot r, which we show down here. And so when we put everything together, we get this. We get that when we add up 2 waves and then multiply them by each other, so we compute E star E, where was that? E squared up here. If we have these 2 terms and we add them and compute E squared, we get the intensity of one term, the intensity of the other, and then this cross term. If we only had these first 2 terms, wave optics would be incredibly easy. It's this term that makes wave optics hard, but in making it hard, it also enables you to pull all sorts of tricks with interfering things with each other to make a signal strong when you want it to be strong and weak when you want it to be weak. All right, so this is the exact result. This is from following all the steps. Now, we also could have just factored out the time dependence. And if you read a lot of optics articles, that's what they do. Maybe on page 1 of the article, there's an e to the minus I omega t, but by page 2, they get rid of it, and you're just left with things that look like this. And so let's compute E star E now. Let's take the complex conjugate of this and multiply it by itself. And when we do that, we're going to, again, be multiplying 2 things, 2 terms each. So we're going to get 4 terms. We're going to get this times its complex conjugate, that's A1 squared. This times its complex conjugate, that's A2 squared. And then we get these 2 cross terms. And the cross terms, of course, have A1, A2. And they've got these exponentials with differences of k vectors in them. And so we get the exact same thing as before. And it comes at a price. The price is that we have to factor out the time dependence, which makes the math easier. But when you're new to this in your conceptual picture, you're thinking, wait, does this wave or doesn't this wave oscillate? And the answer is that it does oscillate, but we're sort of leaving it out. We're treating it as implicit. And this is, I think, a much bigger leap than some of the linguistic analogies I was making before. You know, it's one thing to leave out the subject of a verb, but conjugate that verb in a way that makes it clear that it's got to be first person singular, which means the subject has to be I, or something like that. You know, it's one thing to leave out one word, but have everything else be so explicit from all the other words. It's another thing to just say, hey, we're dropping out the time dependence. We assume it away. I think you would be justified in saying, wait, what? And my best justification for that is that it works but it enables you to go from somebody's computer making noise.
Gonna say, Thomas, the choo-choo's coming through.
Luis, your microphone is unmuted. I'm going to mute it. Where are the other participants? I just want to see everyone, see if any other microphones are on. No. Okay. So where was I? So that's how we write out these waves. There's one key difference between what I did here and what we're going to be doing next. What we did here is we assumed that we have two waves coming in with different k vectors. So they're going in either different directions or they have different field spacings. We usually consider same field spacing, different directions. And then we're doing K2 there. So that's one way of doing things. We can add up two waves with different K vectors, but at one point in space, so the same R. It's an easy way to derive these formulas, and it enables us to justify everything we're going to do when we just say that the intensity is proportional to 1/2 E star E. But a lot of the time what we're going to be doing in wave optics is looking at two waves that come to the same point in space. You might say these arrows aren't pointing to exactly the same point. These paths are pointing to slightly different points, but that's just for convenience to distinguish. But these paths started off from different points, from point A and from point B, and then they made it to the detector. So these two waves have the same K, or almost the same K, so close to the same K that we're going to ignore the distinction. Different starting R, so they have the same, final R, so they have different delta R. That is a difference. The math works out. The only difference is that all of these K.R terms, instead of having K1.R and K2.R, we replace K1.R with K.R1, K2.R with K.R2, and we're left to conclude that our intensity is 1/2 A1 squared plus A2 squared plus A1, A2 cosine of K.R1 minus K.R2, or cosine of K dot delta R. Any questions on that?
Don't you need a parentheses to be able to distribute that 1/2 to multiples of those terms?
Oh, yeah. Any other questions? All right, well, at this point, you've got the formulas justified so that you can do certain calculations on the homework. I want you to read ahead on the two-slit experiment in the textbook, and then we'll go over our own approach to it on Thursday. But before we switch to Zmax, there's one other thing I want to show you. And so now I'm going to share desktop 2. And let's see. View full screen mode. Okay, does everybody see a slide that says interferometric lithography by picking between my two shares?
It's loading your screen sharing.
It's loading it.
Yeah, it says Alex Small has started screen sharing, and it's doing that little circular loading symbol.
All right, well, wait a moment.
Yeah, myself, I'm still looking at the Blackboard submission screen. Is anybody seem to be stuck on that one?
You want desktop or which platform?
Oh wait, my desktop sharing is paused. Okay.
There we go.
Now
Now I
you're
see it.
interferometric lithography?
Yep.
All right. So there are cases where people do useful things with two waves that have different Ks but the same R. Let's imagine that we've got two waves coming in, different Ks, and our intensity, if we assume that the intensities of the two beams are the same, so that A1 and A2 are the same, we can simplify it to 1 plus cosine of delta K dotted with R. Now, if you look at that, we got the cosine of something times position. So the period is just 2 pi over whatever is multiplying position in that cosine. So we're going to have points of high light intensity and low light intensity, and they're alternating. All right? And there are chemicals called photoresists, which are used all the time in the semiconductor industry, which are light sensitive. If you expose them to light, then depending on which type of photoresist you use, either the resist will become much more soluble, so anything that was hit with light can now be dissolved, or it will become less soluble, so anything that was hit with light won't be dissolved. But either way, you can produce a pattern where you've got places with photoresist and places without. And the spacing between these things is going to be hundreds of nanometers. And there's a lot of interesting optics that you can do if you have a structure where the spacing between high index and low index materials is a few hundred nanometers. You basically have the optical equivalent of a crystal. In a crystal, you've got atoms that are evenly spaced. And electrons behave like waves on the microscopic scale. And those electron waves do interesting things when they're traveling between evenly spaced nuclei. The nuclei are exerting forces on the electrons. And so you've got a wave interacting with evenly spaced objects that can push on them and deflect them or attract them. Likewise, with light, if you've got evenly spaced high index and low index materials, then you've got this periodic arrangement of things that can transmit or deflect light. So a lot of the physics of electrons in crystals also happens with waves in what we call photonic crystals. And people started doing this interferometric lithography to make these materials certainly by the early 2000s. And one little side project I had in grad school, I had been making things called PDMS stamps. PDMS is polydimethylsiloxane or silicone. It's rubber, it's easy to work with. Silicone is used in a lot more things than just the one stereotypical application that people joke about. It's a very widely used rubber. You probably have silicone in your kitchen. It's commonly used as a protective thing. If you have a lot of lunch carriers have silicone rubber in them. One thing you can do with silicone is that you could make silicone, you can have some photoresist. You pour silicone between the photoresist. And so now what you've got is silicone with, there's two ways you can do it. You can use the silicone to shape the photoresist or the photoresist to shape the silicone. But you've got, in the end, silicone with little channels in it, and you can flow things through those channels. That's called microfluidics. But you could also, like I said, use the silicone with the channels in it to determine where the photoresist will and won't be. And then you could take the photoresist that got exposed, sorry, the photoresist that got deposited in these patterns, and you could expose it to light like this, expose it to two waves, have them interfere. And what you could make is alternating channels of photonic crystal. So this is a very zoomed out view. This is somewhat zoomed in, and you can see that there are these channels of photonic crystal. If you look really carefully, you can see that there are periodic arrangements of pores on there, maybe a little more visible from the side view. And this is zoomed in to show just how regular and periodic those arrangements of pores are. And so we were doing this in grad school 15 years ago to make essentially waveguides, to make wires for light. Anyway, that's one application of this interference principle where you take two different Ks and interfere them at one R. What we're going to talk about on Thursday when I will start holding full-length classes is what happens when you've got one K and two Rs, two waves that traveled the same path. It's just that one of them went a little farther along that path. Any questions on anything?
No.
All right, then let's go to Zmax. Let me figure out how to get out of this. There must be some way out of here. Pause the screen share, resume the screen share. I want to minimize Zoom somehow so that I can go to another application. Well, I'll just go to there. So everybody go into Zmax and pull up some kind of single thin lens. Some simple thin lens. I don't care very much which file you use. I just want to make sure we're all on the same page. I'll give everyone a minute to do that.
Are you going to ask us to screen share our Zmax?
If you have questions, if your question is of the form, I'm doing X and it isn't working, but I'm not going to ask all 20 of you to screen share at once. That would create a lot of bandwidth issues.
Okay, because remember I'm on tablet.
Yeah, but if you have a Zmax question, then I'm willing to take it. So, all right. What we're going to be doing is, I had told you last week that the way lenses work is that at very narrow apertures, it's diffraction limited, and at very wide apertures, it's aberration limited, because we found when we played around in Zmax, if we had a very good lens and a very narrow aperture, then you saw something like, move my Zoom window out of the way, we saw something like this. Oh, very different from that. Let's make it like that. That if we had a very narrow aperture, And let's go to higher sampling so that we can really see the ripples. All right, you would see those ripples in there. And that if we made the aperture a little bit wider, here, let me go to a PSF cross-section. And whenever you have something that's choppy, just up the sampling. But be careful not to up the sampling too much, or you may be waiting a very long time. All right. And then we found that if we narrowed the aperture, widened the aperture, the PSF got a little bit narrower. But then if we kept widening the aperture, it goes from getting narrow to getting very wide and no longer, let's normalize. Normalize just means we set things so that the peak is always 1. It becomes wide and it no longer becomes a nice ripple pattern. It becomes a much messier pattern, which is a sign of aberrations. So there's a crossover. And when I did the assignment, I got a crossover. I played with the aperture, and I found that for narrow apertures, if I did a log-log plot, it went down. The spot size decreased as 1 over the aperture. And then as I started to widen the aperture, there was a crossover where it eventually went from getting narrower to getting wider. The point spread function became wider. And it's actually much more complicated than R cubed. If you just do geometrical optics, you just look at rays, then you get a very nice R cubed dependence on aperture size. But once you start doing the wave optics calculation, the most realistic calculation, everything is messier. So you're not going to get that the spot size is proportional to exactly aperture cubed. You're going to get something between aperture squared and aperture to the 4th, depending on details. The really key thing is that there's a crossover, and your assignment is to find that crossover. And one thing I want you to remember is that if you just look at the width at half max, that might not be helpful because there's always this central peak, always. But if the light is really spread out, the width of that central peak isn't telling you much because yes, there is a central peak. Yes, there is a halfway point on that central peak. But anybody doing an experiment is not going to see many effects from that central peak because there's so little light there. With so little light there, you're not going to actually detect much. When you look at it here, your view is dominated by the outer rings. So to figure out something that's relevant to a real experiment, it makes more sense to look at an enclosed energy graph. This graph is basically telling you what fraction of the energy will you see if you go out this far. You know, if I were to go just look in this ring, only a little bit of the energy is contained. If I go out here, more energy is contained. If I go out there, even more energy is contained. If I go out here, something like 99% of the energy is contained. And that is what this graph is showing you. But there's one caveat. If we think about aberrations, every time we change the aperture width, the focus shifts slightly. So we should always do a quick focus. It only changed the layout a tiny bit, but if we look at our diffraction circled energy, it goes from being this thing. Let's take a while to calculate. We have a wide aperture. Wide apertures give messy field patterns that take longer to calculate. Okay, 99% done. Yeah, it did get somewhat better. What we were really seeing here was just the effects of being out of focus. And so to figure out whether you're seeing the effects of aberrations or being out of focus, and they look very similar. I was telling you that it was an aberration because it sure looked like that to my eyes, but you never know for sure until you do the quick focus. So what I want you to do is set up a very simple thin lens and optimize it for rays from infinity. And then once it's been optimized using a merit function for rays from infinity, calculate the diffraction and circled energy, then change the aperture, calculate the diffraction and circled energy again, and keep on doing so until you've mapped out spot size versus aperture for a pretty wide range of apertures. I find that a good trick for doing something like this is we're trying to find a power law. When we try to find a power law, it's better to make a log-log plot. But on a log-log plot, if you want things to be evenly spaced, think about what happens with logarithms when you multiply two numbers. And now I'm going to try to switch back to my tablet where I can write, share my screen, and I will go back to OneNote. Okay, if we think about logarithms, the log of a times x is equal to log a plus log x. And the log of a squared x is equal to log of a squared plus log x, or 2. By the way, are you seeing my tablet or are you seeing Excel?
We're seeing your OneNote. You're fine.
So 2 log a plus log x, and the log of a cubed x is 3 log a plus log x. So basically, every time you multiply something by a, you shift the logarithm. You just add the same thing to the logarithm. So log of a to the n x is n log a plus log x. So in Excel, let's go back to that. I'm going to share what I had in Excel. Let's switch to Zoom and see if Zoom is now showing. Every time I multiply by 1.2, I shift more or less evenly along here. So I go from 2 to 2.4 to 2.8 to 3.6. And this isn't exactly multiplying by 1.2, but I just didn't want to mess around with lots of decimal places. So I take these, and then I, again, each of these is 2 times something down here. So 4 is 2 times 2, 4.8 is 2 times 2.4, 5.6 is 2 times 2.8, 7.2 is 2 times 3.6, and to 8, which is 2 times 4. And I keep doing that. I keep going in those steps. And things aren't perfectly spaced along here, but they're more or less evenly spaced.
Hold on real quick. You lost me. You're starting at 2 on your aperture, and then you're multiplying by 1.2 each time to get those aperture values, or?
Yeah, and if I multiply by 1.2 4 times, 1.2 to the 4th, let's just do that, equals 1.2 to the 4th. 1.2 to the 4th is roughly 2. So I don't quite multiply by 1.2 because 1.2 times 2.4 is not 2.8, it's very close. It's actually 2.88, but that's close. And 1.2 times 2.8 is not quite 3.6, but it's reasonably close. And I should have done 3.4, I just realized. But I didn't. I did 3.6 by mistake. But what I have is I have a range of more or less evenly spaced values between 2 and 4. And then I multiply these more or less evenly spaced values by 2. And so even though things aren't perfectly evenly spaced here, they're pretty close. And that means that when I fit a line to this log-log graph, I can be reasonably confident that what I'm doing is reasonable. And I did this, I should have done 3.4 here instead of 3.6. That was a screw up. But if I change it now, then everything's going to look a little bit weirder. You see how it gets kind of jagged? So I should stick with 3.6. But the same basic idea applies. So that's what you're going to be doing. You're going to be playing around in Zmax, getting the width. And now I have to change my screen share again. I need to shift to that. Okay. You're just going to be playing with the aperture and seeing what happens on this graph and make a couple of plots. Any questions?
Yes, Dr. Small.
Yeah.
Earlier you said we're going to be using the optimize function when doing this, but what are we setting as the variable for it to optimize with?
What we're going to do is we're only going to optimize the lens once. We're going to optimize the lens when it's at its full or almost full aperture. And let me double check what I wrote in the assignment before I answer that. Oops, wrong file. So I said, you're going to optimize Wavefront. So what you're going to do is we're going to start off with the lens being almost optimal, almost full. I said what? Outer diameter of 40. So you will set this to, let's say, 38 or so. Did I give a specific number? 39. I said that. So you're going to select the, you're going to set the aperture to 39. And we are going to do, we're going to go for a focal length of 100 millimeters. So we're going to make this last layer thickness 100. And then we're going to optimize in our merit function. Why is our merit function there? We're going to optimize wavefront, not spot size. And the reason we're going to optimize wavefront is because now we're trying to get a diffraction limited lens, or we're trying to get as close to diffraction limit as possible. And of course, we're never going to perfectly get there. Actually, you know what? I'm going to give you a choice. I know I wrote wavefront in the assignment, but I think it's more interesting. I'm going to give you a choice. to optimize spot size or optimize wavefront, and just see what happens in each case. All right, because if we optimize RMS spot size, let me
Wi-Fi sucks.
yeah. If we optimize RMS
Terrible.
spot size, let's look at the lens data and see how much things change. It barely changes. The curved surface goes from 62 point something to 62 point something else. Whereas if we go with wavefront, okay, we apply that, 62.99, start, exit, 62.98. So yeah, this surface changed from 397 to 400 something, which in absolute terms is a big number, but it's the flattest side. So it goes from being very flat to slightly more flat, whereas the most curved side, where most of the action happens, went from being this curved to about 0.01% more curved. I'm not going to worry too much about it. But either way, you optimize this lens so that it's giving its best possible performance, whatever that might be, when it's really wide. And once you've got it optimized, we look at the diffraction circled energy. And it's a bloody god-awful mess, but there it is. And we say, all right, at this distance from the centroid, we get 50% of the energy. Write it down. Then we go to a different number. And we try again, or we start on the other extreme. Let's go to the narrowest imaginable aperture. And we did a very high sampling level simply because we had a very wide lens before. So we got a very messy pattern. We had to sample a lot, and it's going to take it a while.
You mean I have to wait for a buffer that's not my internet?
Yeah, here's, you're waiting for something that is not your network. It's just Zmax taking forever to calculate this at a high sampling level. You have to use a high sampling level for wide apertures. You can get away with low sampling for narrow apertures. So as soon as this is done, believe me, I'm going to change the sampling.
So just while this computes what it's doing, I just want to confirm we're going to be using the same radius from the centroid for all the data we grab, right?
Yeah, we're not re-optimizing each time because we're pretending we've got a single physical object made out of glass. We design it, then we pretend that we made it, and now we just see what it does. So we're not going to re-optimize it each time. Because if we re-optimize it each time, we're doing a different lens each time.
We're
asking about a different piece of glass each time. All right, this looks bad. But before we, 128 is much faster. All right. It's still, it doesn't look nearly as good as you would think for the narrowest aperture. But if we look at it over here, it's out of focus. Those rays are still coming together. So we won't change the radii of curvature each time. We're going to leave the radii of curvature alone. We will change the focus. We will do a quick focus each time because we want to bring those rays together. And now it looks focused. I had to zoom so many times before it came in. And now when I look at it, I get something that looks much nicer. you see that the actual performance at 0 degrees is perfectly overlapping the diffraction limit curve, which is exactly what we would expect for a narrow aperture. Whereas for an intermediate aperture, we see that they're almost overlapping. And if I go up more,
Miguel, mute yourself.
did I mute myself?
No. Miguel needs to mute himself. We can still hear dogs or something in the background.
Okay, when I go to this intermediate aperture, I notice a discrepancy. If I do a quick focus, part of the discrepancy goes away. Not all of it, but part of it. And so you have to do a quick focus each time, because we're going to assume we don't change the radii of curvature. We got the same hunk of glass from start to end. But we do a quick focus because whatever aperture we're using, we would be setting up our lens system to be focused for that aperture. Any other questions?
No, sir.
All right, so here's what I'm going to do. I'm going to stay logged into Zoom for the next hour. I'm not going to introduce any new material, but I'm going to stay logged into Zoom so that anybody who wants to work in ZMAX can, at any point, share their screens with me. And I'll just be logged into Zoom so that you can unmute yourself, say, Dr. Small, I want to screen share. We'll figure that out. And we'll take a look at it. But otherwise, I'll just be sitting here at my desk doing whatever work. I'm going to upload the lecture recording. Actually, what I'm going to do is I'm going to log off and then log back into Zoom. Because I want to log off so that this 1 hour can be saved and processed and uploaded to YouTube. I don't want to upload to YouTube the next hour of me sitting here and people occasionally saying, Dr. Small, I want to share my ZMAX screen with you. Okay. So I'm going to stop recording and end the meeting, and then I'm going to restart a meeting. So just bear with me. I'm going to end this meeting, and then you're going to see it again in a few minutes. Save that. Close that. ZMAX is still there. Bring Zoom. Oh, well, wrong thing. All right. More. All right. I'm ending the meeting. I'll be back in a minute.